Hi, year 8. So start off with a retrieval roulette. So open up your workbooks and answer those questions for me, please. So pause the video, get them answered. Do you have those done? Promise? Okay. So here's your answer. So again, pause and get these marked and corrected. There's one thing I do want to point out. See there in question 6, CO2, carbon dioxide, that wee 2 should be a wee small 2. So you've seen the way that's written in the notes and on the knowledge organizer, that's how that should be written here. Just hasn't formatted here in Excel. Okay, now if you open up your notes at page 45, that's the workbook questions that we were doing last week, and open up your workbook. It should already be open, but open up that, turn back to your workbook questions, get a different colour pen than you wrote in, and then you can mark and correct these questions. So we're going to spend a bit of time going through those today. Right, so question 1. See, whenever I'm going through these, I've written down the side where I've got my answers from. Just remember, whenever you're answering these questions, it's fine, flick through your notes, get the answers from your notes. So because some of you are maybe forgetting that, I have just written down the side of all my answers where the answer can be found. Now for a bunch of them I've written KO, that just means knowledge organizer, but this information will also be in your notes. I just think it's maybe easier to find it from that knowledge organizer sheet for the energy topic. Okay, so question 1, the definition of a renewable energy source is energy that is collected from resources that will never run out. And in a lot of these questions you'll see I have underlined in red like the important bit, or the if it's a fill in the blanks I've underlined the blank, but the key bit of the answer I've underlined in red. Question 2, what's the definition of a non-renewable energy resource? So a non-renewable energy resource is an energy source that has a finite supply, like the opposite of infinite, and it will run out. 3 was asking for the definition of efficiency, and again I've got that from the knowledge organizer. So it's a measure of the proportion of the input energy into a system that is converted to useful output energy. 4 had asked us to name the non-renewable energy resources, and again I've got that straight from the knowledge organizer: coal, oil, gas and nuclear fuel. 5 had asked to name the 3 fossil fuels. So again, knowledge organizer: coal, oil and gas. Remember, pause this. If I'm going too quick, make sure you pause and get yours corrected properly if they need corrected. 6 wanted us to name the renewable energy resources, and again I've just gone straight to the knowledge organizer for that. So solar, wind, hydroelectricity, tidal, wave, biofuel or biomass. I'm not sure if it's mentioned as biomass in your notes. These two can be used to mean the same thing. My habit actually tends to be to say biomass, but the notes mostly say biofuel, so I just wanted to make sure that you knew what I was on about if I said biomass anytime, and geothermal. One thing I do want to point out here, be super careful, like for this you would never just say water, because water is used in hydroelectricity, tidal power and wave power, so it's used in lots of different ways. So if you just put water as your answer, that's too vague. Okay. So 7 was asking for a disadvantage of all of these things. So the first one, 7A, disadvantage of burning a fossil fuel. So I maybe haven't listed everything, but the big one is that burning fossil fuels will release carbon dioxide or CO2 into the atmosphere, and that's going to contribute to global warming. So you can see here I got that information from page 39 in the notes. The next one we had been asked about there was the disadvantages of wind power, and here's what I've put. I've got this from page 42 in our notes. It isn't always windy, so that means that wind power can be unreliable, or you could say it's an inconsistent supply. It can also harm birds. The blades going around, the birds can fly into them. C was asking for the disadvantage of solar power, page 43 in your notes. So solar power, you're not going to get any electricity produced at night time whenever it's dark, and you're going to get less electricity produced on cloudy days. It's not that there's none produced on cloudy days, but there's definitely less. So again, similar to wind, you don't get a continuous supply, or you could say it's unreliable. D was the disadvantages of hydroelectric power, page 42 in your notes. It can disrupt the local ecosystems, the way it has to be built, and because it has to be somewhere where like the water can flow down, it is only suitable for some areas. You need to have that landscape. E then was the disadvantages of nuclear power. So the big one for it is that it creates radioactive waste, which is very, very dangerous. It's very difficult to dispose of, and if there's a natural disaster or an accident, then that radioactive waste can get out into the atmosphere of the surrounding area, and that's not good. So page 39 was where I got that information from. Okay, so question 8 here was about this pie chart, and it shows the proportions of electricity generated in the UK from different energy sources in 2010. Calculate the percentage of electricity generated using fossil fuels. So if we look over here, nuclear isn't a fossil fuel, renewable not a fossil fuel, coal is, and gas is. So we just had to add those two percentages together, and that got us 77%. For part B, we had to fill in the blank in this sentence. So in some types of power stations, fossil fuels are burned to heat water to produce steam. And again, I've got that from page 40. Part C, fuels releases carbon dioxide into the atmosphere. Why do many scientists think adding carbon dioxide to the atmosphere is harmful to the environment? Well, burning fossil fuels releases carbon dioxide, or CO2, when it's burned, which contributes to global warming. And two of the fossil fuels are coal and oil, and they produce sulfur dioxide, which the chemical symbol for that is SO2, and that can cause acid rain. Now question 9, you'll see I've highlighted a few wee bits and I'll explain why. Let's read it first. So the graph, this one, gives information about the production of electricity in the UK in 2016. The UK government signed the Paris Climate Agreement in April 2016. The agreement commits the UK to reduce the amount of carbon dioxide released into the atmosphere. Explain which energy resources in the graph should be used to meet the UK's commitment to the Paris Climate Agreement. So see questions like this with a lot of words in them. Sometimes I can read the whole thing and then not have a clue what it's asked me. So after my first read through, if it's a whole load of numbers, I'll make my list of information, you've seen that. But if it is just all words like this, I'll go back and I'll make sure that I understand what on earth the question's even asking me for. So in this one, here I've seen the word explain, so I've honed in on that. So explain which energy resources in the graph, so it has to be from these ones here that we're talking about, should be used to meet this Paris Climate Agreement. Now, let's remind ourselves what that is. So if we look back in the question, it tells us what that is. The agreement commits the UK to reduce carbon dioxide. So by picking out those key bits of information there, I now know I need to talk about how which energy resources we can use to reduce carbon dioxide, and it has to be from these ones. So the only ones that we can use to reduce carbon dioxide are nuclear, it doesn't release any carbon dioxide, and wind, because gas and coal do. So that's what I've written there. To reduce carbon dioxide in the atmosphere, we would use nuclear and wind. For B, on average there's enough wind in the UK each year to supply all of the UK's electricity needs. Explain why the UK may still need power stations that use fuel to generate electricity. Well, the problem is that it's not always windy, so let's see what I put for that one. So even though there's enough wind in the UK to supply all of the UK's electricity needs, the UK may still need power stations that use fuel because wind is not consistent. So electricity supplied from wind cannot be consistent, and that means it's unreliable. It will not provide a continuous supply. So yes, we can use it, it's brilliant, but we need like a backup plan for those times whenever it's not windy. Now question 10 is an interesting one because there's nothing in your notes about shale gas, but now we've asked about it, but there's information in the question that we need to pick out. So shale gas is natural gas trapped in rocks. Shale gas can be extracted by a process called fracking. There's some evidence that fracking causes minor earthquakes. Burning shale gas adds carbon dioxide to the atmosphere. Describe the advantages of nuclear power compared to the use of shale gas. So we have to talk about why nuclear power might be better than shale gas. So you can see what I've written here. Nuclear power does not release carbon dioxide, and it was mentioned in the question that the shale gas does. It also doesn't involve this fracking process, which is controversial. So it's not going to lead to earthquakes. And the other thing is that nuclear fuel, it says this somewhere in your notes, it must be on page 39, look. Nuclear fuel won't run out as fast as coal, oil and gas will. So nuclear fuel will be around a lot longer, it'll last a lot longer than shale gas will. Okay. 11, another wordy one, not my favourite. calculations are my favourite. So read this extract from a newspaper. Explain one way in which the islanders could try to ensure that a similar power crisis doesn't happen in the future. So some sort of power crisis, we have to figure out, well, what went wrong this time? What should they be doing better? So the population of a small island off the coast of Scotland decided to generate all their electricity from water and wind. However, they did not predict having a long period of warm, dry weather. A combination of low water levels and hardly any wind has drastically reduced the output from the hydroelectric power station and wind turbines. So I was thinking, right, they obviously want it to be renewable, so I haven't recommended coal, oil, gas or nuclear. I've stuck with the renewable energies. So if it's not windy, what could they use? Oh, solar. That's a good one. I put it first. But then I thought, do you know what? Do you know what would be the best in this situation? Biomass or biofuel. Because it can be used very, very similarly to coal, oil and gas. It can be burnt when it's needed, when the electricity is needed, and you'll be able to get a constant supply of electricity out of that. And then you just keep planting the trees, the willow or the poplar is another one that's used. You can keep planting them, they grow really quickly, and then they can be burnt again. So let's see what I wrote. Bet you haven't worded it very well. So they could have used a variety of energy resources, they could have a variety of energy resources in use. So solar power would be suitable for a long period in summer because they had mentioned the warm, dry weather. I thought, well, that was probably going to be the summer. So if they had solar, that would be like a good what's the word, like the opposite whenever it's whenever there's not much wind or there's not much water. It's likely there's going to be a lot of sunshine. But I do think this one here is better. So biofuels or biomass could be good to use in situations like this because it can provide a continuous supply of energy when the conditions are not right for wind or solar or tidal. It'll work whatever the conditions are and it is renewable. Oh, I forgot to say for question 11, that was me just looking through all the notes on page 41 to 43 to get that because that's where all the renewable stuff was listed. Okay, question 12. Energy can be stored in a pumped storage power station. This diagram shows a pumped storage power station when electricity is needed. The water in the high level reservoir is allowed to flow down to the low level reservoir, and then the flowing water is going to turn this turbine here, and that will turn a generator, and the generator will generate electricity. What we had to do in question 12 was to fill in these blanks, so I have done that here. So the water in the high level reservoir stores gravitational potential energy. The flowing water has kinetic energy. The water turns the turbine, which is connected to the generator, and the generator raises the thermal, remember that's just another word for heat energy, of the surroundings. I had initially written heat in here, but it wasn't in the box, so I had to change it. So I got that information really, I suppose, from the knowledge organizer or our very, very early energy notes, like just the energy definitions. Right, part B. So the total energy input to a pumped storage power station is 600,000 joules. As soon as I start to see numbers in a question, I'm thinking I need to make my list of information. Then it tells us the useful energy output is 540,000 joules. Part 1, calculate the efficiency of this pumped storage power station. So here's what I did. I've made my list of information from the question. The total energy input was 600,000 joules. The useful energy output was 540,000 joules. And then it's asked me for the efficiency. So the first step in my working out is to write out my efficiency equation exactly like this. So efficiency equals useful energy output over total energy input. Now that I have this listed up here, it's really easy for me to pick out what values go in. So useful energy output is this 540,000, so that's gone in there. Total energy input is 600,000, so that's gone in there. I type this into my calculator and it's given me 0.9 or 90% if we want to give it as a percentage. So this information, if I was stuck, I could have looked through my notes. I would have found it on page 26 in my notes, the efficiency definition and equation, or I could have got it from my knowledge organizer. Hopefully you're starting to see that having your knowledge organizer out as you're working could be very, very useful because all the key information is there. Part 2 then goes on to ask us calculate how much energy is wasted by the pumped storage power station. So that's just the total energy in, take away the useful energy out because the rest must have been wasted. So once I did that, I got 60,000 joules. Part 3, how is the temperature of the surroundings affected by the energy wasted by the pumped storage power station. So there's my answer for it. The temperature of the surroundings will increase. The energy wasted as heat will heat up the surroundings. Now you'll notice here I haven't listed where I've put those from, and it's because that's really just using your, I want to say common sense, but thinking it through logically is really where we get that from. Okay. And then last question, part C, if the power station takes 2 hours to produce the 540,000 joules of useful output energy, what is its power? So again, if it's asking me to calculate something, I'm making my list of information. So I'm listing my time and my energy. So I'll show you that. So the time was 2 hours. And see, whenever I wrote that, I've had a quick glance and I've looked to say, oh, that energy's in joules, right? If my energy's in joules, my time has to be in seconds. So to go from hours to minutes, we multiply by 60 because there's 60 minutes in an hour. And then to go from minutes to seconds, we multiply by 60 again because there's 60 seconds in a minute. So that's why I've done this, and that gets me 7,200 seconds. The energy was 540,000 joules, and it's asked us what the power is. So my equation, which I've got either from my knowledge organizer or from page 34 of my notes, is power equals energy divided by time, or energy transferred divided by time. Substitute for my energy, which is the 540,000, and my time, 7,200, gets me 75, and my unit for that is watts. So that is our energy topic finished. We will be giving you a little quiz on that soon, so you've got that to look forward to. But because going through those answers and correcting your answers is quite information dense, we're only going to do a little bit of our new topic today. Okay, so just a small amount to give us a wee taster about this next topic, which you can see is heat. So if you open your notes for me please at page 47, then we will get started. So we've talked about heat a little bit so far within our energy topic, and that's what these 3 wee questions here are to help you get that information back into your head. So if you answer those in your workbook, if you pause me, get those answered in your workbook. Okay, good. So all of this will be in your knowledge organizer. Hopefully that's where you looked for the answer if you couldn't recall it from your head. So let's start looking just today at heat and temperature, and just a little bit of information on the factors that affect how much heat energy impacts on something. So we need to make sure that we know the difference between heat and temperature and that we don't use those words incorrectly. So temperature is a measure of how hot something is, and we tend to, in everyday life, like just use our normal senses. Oh, it's really hot in here, or oh, it's really cold in here. But the problem with that is that 2 people might judge a similar situation very, very differently. Okay, so if you know Miss Mawhinney, she is always freezing. So I could be in a room and Miss Mawhinney could be in a room and I would be roasting and she would be sitting there with 5 layers on and still be cold. So because of that, we can't use our judgment. So we have to we'll have to use a proper measuring system to measure it, and I'm sure you're familiar with this. We use a thermometer to measure temperature. So the units that we use for temperature, like, you know, the way like distance is measured in meters, energy is measured in joules, power is measured in watts, the units for temperature are degrees Celsius. Okay, so we degree symbol and then a big capital C. Now if you see here it says your teacher will demonstrate this, I'll talk you through how you can do that at home. If you can get 3 bowls, okay, so just normal bowls that you would eat your dinner out of or whatever. If you get 3 bowls and if you put some lukewarm water or room temperature water in one of them, hold on, I'll draw a wee diagram to show what I mean. So this is a wee demonstration that you can do that just shows you why we cannot use our senses to judge temperature. So if you get a bowl and you just put some room temperature water, like if you mix the hot water and the cold water together, put that in one bowl. If you put really cold water, if you have ice cubes, put it in to make it extra cold in another bowl, and then if you put hot water in another one, as hot as you can, get it so that you can put your hand in and not burn yourself. Okay, then if you put one hand into the bowl of water with the hot water in it and then you put it into the room temperature water, well, how do you think that water is going to feel? If you've gone from really hot water to really normal temperature water, that water there is probably going to feel much colder to you than it actually is. Whereas if you put your water in this, or put your hand, sorry, in this cold water, and then you put that into the room temperature water, well, compared to this is much warmer. So this is going to feel really, really warm to this hand. So if you do that with your two different hands, then it's really weird, because one hand you put in here and this will feel really cold. The other hand you'll put in here and this will feel really, really warm, even though it's the same temperature for both hands really, but the situation that your hands are coming from has affected how you feel the temperature of that water. Okay, so do give that a go. And it's just a good wee demonstration of why we cannot use our judgment just to measure temperature. Like, we can't say it's really warm in here because we've maybe just come from somewhere really cold, or someone else might have come from somewhere really warm, and then it'll feel cold to them. Okay, next little bit then is heat energy. So generally, the higher the temperature of an object, the more heat energy it will have as a store, and the more heat energy it'll be able then to transfer elsewhere. However, that is also going to be affected by the mass of the material. So again, I'll maybe show you a wee diagram to try and demonstrate what I'm talking about here. So if we have two different objects, okay, so we've just got two blocks of metal, say, right, the same material, everything the same apart from their size. So this one's obviously much, much bigger. So say we had a heat source like a Bunsen burner or something, and we supplied the same amount of heat energy to both of these blocks of metal, then the two blocks are going to heat up by different amounts. So for this wee small one, 50 joules per second, if we were supplying that much energy per second, that might heat up really, really quickly. Whereas that same amount of energy per second for this one, it's going to take much, much longer to heat up, and it's all to do with the way the particles move inside the material, which we'll go into a little bit more detail in the future, but for now, hopefully that makes sense. And whenever you see it drawn out like that, so a bigger material is going to take much longer to heat up, or it's going to heat up less for the same amount of energy that's supplied to it as a much, much smaller piece of material. Now, as well as that, forget this, so I've just hidden that from you, so pretend that's not happening anymore. So say we have these two blocks of material and they're at the same temperature, then this one here will have much, much, much more energy than this one. And it's, again, it's all to do with that bigger mass. So say these were both at 70 degrees Celsius, right? They have the same temperature, but because there's much more of this material at that temperature, this one has a much more heat energy than this one. So hopefully that makes sense. So that's just what these notes are saying here. So however, mass also affects the amount of heat energy stored in an object. An object with a bigger mass will contain more heat energy than an object with a smaller mass if both are at the same temperature. One little thing I haven't mentioned yet that is very important for this whole topic is that whenever heat energy is transferring, it always goes in one direction, and by that I don't mean it always goes up or it always goes to the right or it always goes down, whatever. It always travels from a hotter area to a colder area. That there is very, very, very important. Last little bit then was that wee bit I was talking about supplying the same amount of heat energy. So the amount of energy required to heat an object up will depend on the temperature difference. So by that we mean how cold it is to start with and how hot you want it to get. So the bigger temperature difference, the more energy you're going to require. And the other one then, the mass of the object, the bigger the mass, the more energy is going to be required. Now, it says here that I'm going to show you this video from here to here to explain why a bigger mass requires more energy to be heated. This video is long enough, so I'm not going to make you watch another one. I will just talk you through it. So what the lady does in that video is she shows or she explains using the comparison with money, which I actually really, really like. So let's say I have £20, right? And I say, right, Jay, I'm going to give you this £20. You're going to get £20. Whereas if I say I'm going to give £20 and it's going to be shared across this whole class, well, each person in the class is going to get much, much less than £20. And it's the same idea with the energy transferring from to smaller objects or to bigger objects. So I'll just draw a wee diagram here, which I would like you to draw in as well, to try and help explain that. So let's say we've got 2 beakers of water. Now, whenever you're drawing this, can you please draw the exact same number of particles as me? You're going to think I'm very fussy, but you'll see why. So can you draw a wee smaller one with 4 wee particles drawn in it, and then a bigger one with 10 particles, and then draw them both being supplied with 20 joules of heat energy. So draw those down now. Okay, so if I supply this beaker here of water with 20 joules of heat energy, well, each one of these particles is going to get 5 joules each. Yeah, so because there's only 4 particles, each one of these particles is getting a big proportion of this 20 joules of energy, so they're going to heat up really, really, really fast. This one here, which has the 10 particles in it, they're sharing that 20 joules amongst 10 particles, so each particle then is just going to get 2 joules each. Okay, so hopefully you can see like what I meant with the money. It's the same idea. Because the smaller one has got less particles to heat up, each particle gets more energy, so it heats up faster. The bigger one's got way more particles to heat up, so this here gets spread much more thinly amongst them. Each one gets less and it takes much longer to heat up. So we'll write that out here as well. Right, so hopefully the way I've worded that makes sense. So a bigger mass has more particles to heat up, so each particle gets a smaller proportion of the heat energy, so will take longer and therefore more energy to heat. So pause and get that written in. Right, last thing for today then is the questions on page 48. So I need you to answer those. Now, because there is space here on the sheet, you don't have to answer these ones in your workbook. You can answer these on the page. So filling in the blanks here. Do a wee explanation for these 3 things relating to different masses heating up different amounts. Be careful with this one. Complete the table by picking one or both. So whether it's heat energy or thermal energy this statement is talking about, or whether it's temperature, or whether it's both. And then the last wee one is asking again about that mass thing. So use the ratio of the numbers. Remember here, just to remind you, 4,200 joules, but then this asks for in kilojoules. So let me just remind you here that 4,200 joules is 4.2 kilojoules. Okay, so I don't know why they've asked it in a different unit, just to be awkward. Okay, then if you send your teacher a picture of your page 48, and then that's you done. Okay, bye.